Alright, hell yeah. So we got material mechanics and we got sign convention. And we do it in this video. And we make some huge assumptions that are actually kind of wrong. But then we do correct them and we go full depth analysis. So sit back, relax, and we got sign convention. Alright, hell yeah. We got material mechanics and we're going to go over sign convention. I'm going to leave this up for a couple seconds and then I'm going to go to the next page. Leave this up for a couple seconds so you can pause and read through that. But what we want to do is just have an easy. We want to make this as easy as possible. We want to know the sign conventions just within about 2 seconds. And so what we're going to do is we're going to take a beam, and what they say is if you put a force on it, it's going to smiley face. So cool. Once we get this smiley face, we know that this is positive bending moment. You know what I mean? So the moment is positive. I think that is going to be easy. Now, how do you figure out what your shear, what's going to be positive and what's going to be negative shear? So I think this will be an easy way to demonstrate it. So if we make this beam like this, you know what I mean? Now, now we could chop it into little sections. So we are going to kind of do that same smiley face, but now our little sections we're gonna do like that. And I probably shouldn't go too crazy. But now, if we do something like that. Well, I mean, I guess we're learning on the fly. So I don't know what type of axiom, but I do know if you're going to drive a car across a bridge, you know what I mean, and the car's right here, this part is going to go lower, so you're going to have something like this, and then this is going to induce positive shear. So over here, this shear is positive, you know what I mean, if the right side is lower. And then this shear is negative. I guess, I'm sorry for the pause, but there might not be a very good mental. I was just thinking, this is a good way to show like what side is lower and higher. So you get your curve, and we could do the opposite. Because the opposite is like, hey, let's do a cantilever with some force on it. It's going to look, you know what I mean, like this. And then so you could do the same thing with your chunks. You could have that, and then you could have the chunk here, and then the next chunk there. And so essentially, we're going to have downward to the right. So this is going to be positive and shear. Now the bending moment is a smiley face. Just overall, it's the bending moment's a frowny face. So we know the moment is negative. Okay, cool. And then so I guess that's it. You know what I mean? And but one of the biggest hiccups I ran into is just like, well, if we do the shear diagram for this, so we're going to do the shear diagram, and here's our, the shear is going to be a positive shear, because we have positive shear throughout the entire length, so we have something like this. Now, I just got confused for at least all night, and I was just like, well, but if we calculate the max moment, you know what I mean, so the easy thing to do is just cut this out of space. And then once we do, it's floating in outer space, but we still have this force P on it. You know what I mean? But it's not traveling across the galaxy this way, so we need to balance that force. And so we do know that we have a shear force in that direction. and then so this would induce a couple this way, but we do know that it's not spinning. You know what I mean? Visually, this thing is fixed and stationary, so it's not spinning this way, so it must have a balancing torque this way. So here we have a moment that's that direction. And sign convention from a free body diagram perspective, well, this is going to be a positive moment, but we know from the convention that it doesn't matter. You know what I mean? If this thing looks like a frowning face, the moment is going to be by convention negative. You know what I mean? So that's just something to get used to. Taking your free body diagram idea of what the moment is going to be in this direction, which is inducing a counterclockwise moment, which we call positive, but because it's part of a frowny face, this moment is negative. So then we can know from our diagram that this moment has a negative max there, and then by cutting it into more pieces, we know that there's no moment over there. But I guess the take-home point is that, hey, you kind of have this negative area down here, and you have a positive area up there. Well, what gives? You know what I mean? And I just got confused just for a little bit, because I was like, well, how are these graphs related? Well, it says that the slope of this line is the value of the shear. So see how this is a positive slope? So the slope is positive. That means we have a positive shear. I was just used to some of the moment diagrams, because let's do one for just a beam where we have a load in the middle, and I guess I'm not going to run through it too much, but if we're going to have a positive shear and then a negative shear, and then we're going to and then for our moment diagram, sorry about this, but we're going to go up and then down. And yeah, I guess I just got confused. I was just like, well, I got confused from the perspective of, like, what are you integrating? I was thinking, well, if you're going to find the area under the curve, and I guess that makes sense. You're integrating the shear, so you would say, hey, like right here we have no area. So starting here, even though this line goes high, we still have no area. The second we come right here, we have a little slice of area, so just a little bit. And then we keep adding on. And I guess if you do that, I mean, this is why calculus, even just at the most basic, I mean, yeah, you could learn how to find the volume of all sorts of three-dimensional objects, spheres, and blah, blah, blah. But it's just even the basics of, like, well, what's the area of a rectangle? Well, you're going to start to add those pieces up, and you're going to add this area. And then when you do, you're going to get that value, and it's going to be the area. The area is this value along the line. You know what I mean? So if we add up all the area, we will get to that point. And the area is a force times a length. And that makes sense. You know what I mean? And even I'm just learning on the fly, and it's like, you know what I mean? But there's plenty. Like, I guarantee there's plenty of engineers that are just like, give me the equations, give me the unknowns. That was kind of my style. But then you're just like, what's going on here? You know what I mean? We're just basic integration is just like, oh, you have a force times a length, and when we integrate the area under curve, well, heck yeah, we get something that's force times length. Well, that's moment. And so, I mean, the area under the curve isn't this area under the curve. No, it's the actual value of this line. So if you if you add these areas up, you get an equation for this line. So then in reverse order, if we have this equation for the line, and let's say it's just x, you know, I mean, y is equal to x, and even just visually, let's say it's just 1/2 x. Look at the slope, it looks like 1/2. So then when we differentiate dy dx, heck yeah, we get a slope of, excuse me. So this was the slope, you know, this is the equation of the line. When we differentiate, we just get a constant, like half. Well, guess what? That's this value right there. And so I'm glad I'm taking my time and working through the kinks, you know what I mean? Because where you just don't have this 100% figured out, but you're just like, hell yeah, I have enough tools to take a breath and then figure it out, you know what I mean? And I don't mind doing it on camera, but yeah, there's plenty of times where you have to, like, pause the camera, think about it, go eat a sandwich, come back to it, think about it some more, even just for basic integration of just like, what the hell is going on here? So the second you get to this point, well, we added up all that area, we have a kind of a high maximum, but then now we're subtracting area, and we're just subtracting just a tiny bit, so we just go down you know, a little bit, and then so once we subtract all this area, but I swear, even just visually, I want to do this kind of myself again, because it is good to go through that area, just basic integration. So let's do that right now, you know what I mean? And I'm going to add more time on the clock. All right, heck yeah. So, I mean, this is what, in engineering, professors don't do this enough to be like, hey, I bet you if you just have the equation x, you know what I mean, and here's your graph, and here's your y is equal to x, you can't chop this up into intervals of 1 and figure out what the integration is. Like, what's the area under this curve? 1, 2, 3, 4, 5. You know what I mean? So we're going to integrate from 0 to 5 of x. And then our value is going to be, our change is going to be dx. I guess integration is saying, hey, we're going to make this so tiny, and then we are basically going to find the volume. Yeah. So it's so fascinating how just even the most basic calculus, like you can learn calculus to a high level, but then you just go back to like, what are we talking about here? Yeah, well, we're just trying to find the area of that little chunk, and then we're going to use this magical thing called integration to add them all up. You know what I mean? And this is where, and we'll take a pause on this, because a 400 level class was what changed my life with math, and it should have been taught first year. It was just like, well, just friggin' guess. You know what I mean? It was basically doing. It was called numerical methods, and I think it even was some of the. I forget kind of the difference. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's saying this. Is it guess? Is just like, well, guess high. You know what I mean? So we're gonna go here. And even if you just did that, even if you just said, well, this is 1, 2, 3, 4, 5, and you added these up, 5, 4, 3, 2, 1. You know what I mean? Well, that's like 5 factorial, but no. 5, 4, that's going to be 9. 3, that's going to be 12, and then 2, 1, that's going to be another 3. So we have 15. So we have an area of 15. But now undershoot it. So now we're just going to go to this point and over. Go to this point and over. Am I messing up? There you go. So 1, 2, 3, 4, 5. Now this is 4, 3, 2, 1, and 0. So now we got 4, 5, 6, 7, 8, 9, 10. So now we have an area of 10. And guess what? Maybe the area is somewhere in between. You know what I mean? So you could just guess in between. It's going to be 12.5, or even this equation. From an engineering perspective, is like, what's halfway between these? I swear, some of the easiest equations are just like, I have to rethink this one. You know what I mean? We'll just add them together and divide by 2. And 15 plus 10. But as an engineer, it's like, these are the things that are just going to like really slow you down. And this is the stuff that I can teach in videos. Be like, oh, hell yeah. This is where these are the things that you need to spend time on, like the super basics. So then when you do complicated stuff, you're just going to be going way faster. And so we got 12.5. So now, what's the actual? You know what I mean? So if we do this, dx, and we do integration, well, we're going to have x squared plus c 0 to 5. And even just right here, could I explain the plus c? Well, it says when right here, what's the plus? I kind of like I like gravity. When you do, like, gravity is 9.8, and that's acceleration, which is dv dt, and then you can be like 9.8 is dv dt, and then separate the variables. So we'll just go dv is 9.8 dt, and then integrate. You know what I mean? And we can go velocity is 9.8 t plus a constant. But when we do like a projectile drop, we're going to drop it from like a building. We know that the velocity is 0. So and at time is equal to 0. So this equation says, hey, it's an equation for velocity and time, but the c is just like, well, maybe you started with some initial velocity. So now this equation says that, what do we have? We have the area. So this equation, yeah. So even that, even though you integrated, you're like, well, what the hell did you even find? Well, we're finding the area. So this equation says, hey, the area is equal to x squared plus c. But how much area is at x is equal to 0? And this is x is equal to 5. Well, we have 0 area. So we have 0 is equal to 0 squared plus c. So at x is equal to 0, 0 squared plus c, we have 0 area. So this means 0 is equal to c. And even that, like every time you do integration, you get a plus c, you know, just don't hand wave it and say, it's usually 0. So I'm just going to think it's always 0. Because then that's going to limit you when your equation is like, hey, what's the area under that curve? And this still has a slope of 1, but now, you know what I mean? At x is equal to 0. Well, in this case, your area is still 0. And I think that would be the case. Because if this is, let's do that one. Y is equal to x plus 1, 2, 3, 3, and then we integrate that. We're going to get x squared plus 3 plus c. And our area is x squared plus 3 plus c. Oh, no. So this is so cool. So our constant integration does apply, because when we throw in x is equal to 0, our area is equal to 0. So hell yeah. So we go area is equal to 0 squared plus 3 plus c, but our area has to equal 0. So we got 0 area at 0x squared plus 3, because this is just part of the equation, plus c. So now we can see that c is negative 3. And if we integrated this, and we'll do it from 0 to 5, you will see, how much time do we have left? All right, heck yeah. So what were we talking about? So yeah, this fleshes out wait, what up? I feel like, oh, we did this wrong anyway. I'm sorry. If our equation is x plus 3, this is x squared plus 3x plus c. So actually, c is 0 again. You know what I mean? So we have 0 squared plus 3 times 0 plus c. I apologize. You know what I mean? But we're tackling stuff that you should have a grasp on as an engineer. But a mathematician is just like, holy Toledo. But even math, it gets, you spend maybe just a little bit of time on this, and then you use it for complex things. And you might forget just like the basics of integration. So, hell yeah. So in our case, this is 0 again, because the at 0 area, or at x is equal to 0, we have 0 area. And so, yep, so that's our equation. So now if we do this, okay, so yeah, so in this case, I don't know how you would actually get a constant of integrate. If you're just trying to find area, like how would you start with some area? I think you would want to yeah, that's fascinating to me. I don't know, like would you start over here? But anyway, so let's go back to this one. And what is the actual area? Well, it's the equation for area is just x squared now. So we're saying x is 5, the area is 5 squared, and the area is 25. Oh, I'm sorry, and like I'm getting bad at integration. You know what I mean? How many mistakes can I make in this video? But yeah, holy Toledo. So if we have the integration of x dx, you know, and this is something that you should always do. You should always change this to the integration of x to the 1 dx. Because then, you know, the most basic rule of integration is you go x to the power plus 1, and then you take this value and divide it power plus 1. You know what I mean? So in that form, plus c, then you can't make mistakes. And this is very helpful, especially when you're like integrating x is equal to -1. You know what I mean? So you get the natural log of x, because you would go x to the -1 plus 1, and that's just x to the 0, so that's just 1 on top. But on bottom, you got negative 1 plus 1. So now you have 1 divided by 0, and you just can't have that. Yep. So anyway, and then that's where you get the natural log. So yeah, so my mistake, this was x squared divided by 2. But yeah, like I said, how many mistakes can we make? But anyway, so now you'd be 25 divided by 2. But obviously we caught our error because we were trying to shoot for an area of 12.5. And overshooting it and undershooting it and dividing by 2, well, that just got us right there. You know what I mean? So there's a lot of physics problems that I'll just do that. And I won't even overshoot and undershoot. I'll just overshoot and call it a day and be like, close enough. We found the area. All right, so and then the area of this one, I mean, we could do that same process, and let's do it. So we have 1, 2, 3, and then we're going to go over 1, 2, 3, 4, 5, and then we're just going to find the area under this thing. So if we overshoot it, we're going to have 4, 5, 6, 7, 8. If we undershoot it, we're going to have 1, 2, 3. We're going to have 3, 4, 5, 6, 7. So let's add those up. 4 plus 5 plus 6 plus 7 plus 8 is 30. And then 3 plus 4 plus 5 plus 6 plus 7. And if you wanted to be fancy, this is 7 math. Where's factorial? I don't even know, so we probably shouldn't even do that. Oh, there we go. So this is 7 factorial minus, is it minus 3 factorial, or is it minus 2 factorial? I don't know. You know what I mean? Let's do them both and learn something. Holy Toledo. Maybe not. Oh, yeah, math 4. Oh, no, I don't know what I'm thinking. No. Anyway, so we have 30 for there, 25 for there. Obviously, halfway in between is 27.5, or it's the equation 30 plus 25 divided by 2. 30. So we have 30 plus 25 divided by 30 plus 25 divided by 2 is 27.5. And this is going to have an equation of x squared plus 3. Integration is going to be, this is going to have an equation of x, you know what I mean, plus 3. The slope of this line is 1, and it hits the y-axis at positive 3. So if we integrate that, we're going to get 1 half x squared plus 3x. And plus a constant, and this is our area equation. The area at 0, that's why if you do these area, like, yeah, it's so bizarre. And I guess I just don't know the fundamental principle of, like, when you're just finding the area under the curve, is C always 0? You know what I mean? Well, what's an example? Because we just did a physics example. Well, if we start with some initial velocity, then no. I just can't think of an example where you'd start with an initial area of something, especially when you're just trying to find the area from this point to that point. But that is and I think I think I know, if you take this all the way to 0, then this equation is just y is equal to x. If you put your origin here, hell yeah, so this explains it. So now this equation is just y equals x. So the integration of it's x squared, 1 half x squared plus c. But now we have area is equal to 1 half x squared plus c. But when we start if we start at x is equal to 3. So if we go 1 half 3 squared plus c, our area at x is equal to 3, if we're adding all that up, is going to be 1, 2, 3. So we would basically have 3 times 3, so it'd be 9. It would be 4.5. It would be the square divided by 2. So this area has to be 4.5, and we get 3 squared on that side times a half, 0.5. And yeah, we still get 4.5 is equal to 4.5 plus c. C is still 0. So I guess I'm kind of confused of trying to make an analogy between this physics example where we could have an initial velocity with an area equation. But let's just go for it, and obviously the area is 0. So if we wanted to find the area of that, we were trying to see if it was 27.5. We're going to evaluate this, and if this is our equation, this is 0, and this is 1, 2, 3, 4, 5. We're going to go evaluate from 0 to 5. So you throw in 1/2 5 squared plus 3 times 5 minus all this with a 0 in it. That's going to be 0. So we got 5 squared, 25 divided by 2, 12.5 plus 15. And we get 27.5. All right, hell yeah. So yeah, all we're doing is just basic area under the curve. And now I'm going to pause because, like, how is that related to the moment? And why did we just do that just to learn this? And let's find out why. And the reason why is because I was just like, well, visually, it doesn't quite look right. It seems like if you added that area, it's like, well, will you jump to there? And then if you added the next chunk, will you jump to there? You know what I mean? And adding all these slices. And then when you subtract that slice, I mean, does it make sense that you jump to there? But I see the problem that I'm getting. I'm equating the fact that we're finding the area under this curve, and I'm making the mistake that it has anything to do with the area of that curve. That is something that I have to challenge myself to not focus on. We're solely focused on the value at that point. And now you can see that when we get to... Alright, heck yeah. So now let's try to make a proof that if we get to this point and we add, if I think this is steps of a stairs, I'm here and I just jump up to the next value to there. Well, guess what? I just took the area of one step. And then I go to the next step. And yeah, guess what? I just took the area of another step. And now you can see that each of these areas makes the next step go up. You know what I mean? If I had something like this, where if I had just a little bit and then I went up here, and doubled it, you know what I mean, to there. So let's say I do have something like that. Well, I take one step, take another step, but now when I take a step, I'm twice as high. You know what I mean? So each step is going to be twice as high. So this shows that that helps me visualize that the slope of this line is the value of this line. And then so if this is the case, now I'm going to double the slope. I'm going to get up to there. But then when I go back to here, so if I do have something like this, now I'm just going to go down this just normal slope and I would get to there. And I don't know if something like this is oh no, I guess with moment diagrams, I think any combination, you know what I mean, because with moment diagrams, you can have this. You can have the moment diagram be a total area like that, and then that means the shear diagram is 0. And how does this apply? Well, it's because you're taking something and then you're just putting a pure bending moment in it. And then, so, yeah, this is a bummer, because now this analogy doesn't apply. Because you could have something in a smiley face, where then if you drew these little sections, you still, this isn't a good analogy for positive and negative shear. Because you could do this and bend it, and there is no shear forces. You know what I mean? You can have pure bending moment in a beam, and when you do your shear diagram, there is no shear forces. It's pure bending. So this is good. I don't know if a video like this is useful when you're trying to go over a topic and learn it, but you're just like, whoa, I'm making kind of glaring errors, but I'm spotting them. You know what I mean? So I think that's useful, but it's just interesting, because it is like, that's why someone's like, can you do bending moment and shear diagram problems? Because they're not intuitive. Even that, I was just like, well, can we come up with any sort of convention that's just 100% foolproof? But So this little diagram of these blocks being lower, that's not the case. You actually have to do the free body diagram and find out if there is a shear force. You know what I mean? So let's definitely spend some time and tackle, you know, the free body diagram. And I guess I can slow down just a little bit. And we're going to say this beam is in pure bending moment. So it is going to smiley face. You know what I mean? It is going to look like that. But now when we do our free body diagram is when we chop it out of outer space. And we do this, technically there's no force. We haven't identified any forces. And let's say the beam is negligible weight. You know what I mean? So it seems like a pretty special case. But again, we're going to chop this out of outer space. And then we're going to see what we know about it. Well, we have a torque on it that way and a torque on it that way. And so those torques are balanced. We have no forces. And so, cool. And that's it. We don't have any forces. And we need forces on a surface to get shear. So now we can chop this in half. And so we're going to chop this half out of outer space. Now again, F equals MA says... well, one side says, hey, are we observing something that's stationary? Cool, that side goes to 0. But then, just by, and then also kind of by observation, do we notice that there's any forces on this? And the only way to make this truly without shear is if we're saying the mass is negligible. Like, wouldn't that make sense? Because else you would have a force in the middle, and then you would have shear. So I think that's a true statement. If you have a beam with negligible mass and we're putting a huge moment in it, you know, we're saying there is no identifiable forces in the, you know, in any sort of direction. So and if there was, and if we identified at least one force, we'd be like, well, the thing's not traveling across the universe in that direction, so we would have to have a balancing force. But we don't even have that. And we do know that we have a moment on that side. So that's the thing. When you chop this out of outer space, you know something about that side, and then you opened up a face. Now, when you open up a face, yeah, by convention, and the convention is if you drive a car over... and I guess the good thing to do would just be a cantilever. If I'm going to drive a car over a cantilever, it is going to go this direction, you know what I mean? And then you are going to have these molecules in shear that way. So this is called positive shear, and that is one convention that I'm at least going to stick to. And then I guess you could do the opposite. If I'm going to drive a car over the left side of a cantilever, well, then those things are going to go that way. And this is going to be... negative shear in that direction. And then if you did this, so this is negative shear on the right, and if you completed this diagram, this is positive. So see how this is down, but we're calling it positive. This side is up, and we're calling it negative. You know what I mean? That's just why from the free body diagram, well, we would call this a negative direction from the free body diagram. And I'm going to use these symbols to designate what we do on the symbol. But yeah, a negative force is what we find there, and then a positive force. But due to sign convention, I'm going to do these little parentheses and be like, hey, when I make sure to go put it on my moment diagram, if I'm saying that's the shear force, well, this is a negative. So over here, we're going to just say we have a right face, and so we're going to say, hey, a downward force is the positive. So when we do this, and this makes sense, because if we do have a beam, and you usually do rollers over here, and this is A and this is B, we would say that we have a AY up, and at a pin connection we have an AX, and we're just going to assume the positive directions. This is positive X, and this is positive Y. And so we have a normal force at B. This is BY. And we're just assuming all the forces are normal. If we find out that this is cantilevered, in that case, and we push down, this acts as a pivot. And then so this is reefing up on this pivot, which means that from a free body diagram perspective, you chop this out of outer space, and so let's do that one. It's got a teeter-totter in the middle, and then we already chopped it out of outer space. We identified one force, and we know that there's another force right here. Well, we can do this. We can pin this to outer space. There's two different things. You can sum the forces, or you can pin it in outer space and know that it's not a pinwheel spinning around. And so if this is where we tack it into outer space, this force is basically right at the hinge. It would be trying to like open a door at the hinges. This not helping like spin this thing. It's not helping opening the door. Well, this force, hell yeah. And it's a distance that far away. So if we have that negative spin this way, this is going to cause it to spin this way. We need something to balance. So we need a positive torque. So we need to have a force down over there. So in that case, our reaction at and that's the same thing. This is the beam, and the force is on the beam. In this case, we have a force, with the B in the middle, at B. We have a force down, and that's going to be that direction. But this AY is going to be negative P, because if we're showing it in this direction, well, it's opposite. So that's just the sign convention when it comes to free body diagrams. But again, we have to know that we're shooting for the moment diagram, and that's why I do these little parentheses, because then I know how to throw it on the. Because let's say I don't throw a V here, and I just say, hey, I just want to kind of know the forces over here. All right, heck yeah. And so I just assume they're going to be positive. You know what I mean? I'm just going to say, hey, what's the force over here? And then I find that direction of the force. Well, cool. That's useful from a free body diagram perspective. But when we do our shear diagram, and that gets full circle, because if we do the shear diagram, it's a perfect representation. If it's a positive shear, then we're going to get, that means that our moment has a positive slope. But let's go back to the cantilever. So we're going to take a quick kind of pause from this. When we do have this, it's so fascinating. We do the free body diagram and we get a positive shear. And so, and I think I have to just be cautious and just get the shear from the free body diagram. I was saying that you would have kind of the blocks like this. And to a degree, you can do that. You can be like, whoa, we have a force on this right side. So it is like we have a car right here too. You know what I mean? And then this side goes down. And we can visually see that. So it does apply. It just doesn't apply when we apply pure bending moment. And that's what we're kind of analyzing here. When we apply pure bending moment, there is no forces. You know what I mean? We're applying the torque from the side. We're bolting bolts. We're welding bolt heads to this and then throwing wrenches on it and then wrenching up and then wrenching up. It's not synonymous with any loads actually on the beam itself. And so, and in this case, you get a positive shear, but your bending moment is going to be negative. You know what I mean? And again, it's in the negative direction. But this slope is positive. So this slope is positive slope, and that's the value of that shear. So that's what we're going for. And so when we identify the moment diagram, we are going to put this V in the positive direction due to sign convention, because if we do find a force on it, and the force actually turns out to be that direction, well, we know that we have a negative shear. You know what I mean? But for all intents and purposes, this is the positive direction, and if we do find that it's in the opposite direction, if we do find that this value has a negative, well, we know that it's a negative shear. But guess what? There is no forces. You know what I mean? So we have this moment over there torquing it that way. If this was free floating in outer space, we would, and it had just this moment, we would expect this would be a pinwheel just spinning, you know what I mean, with angular acceleration. But we don't. It's got to be balanced by another moment, and that moment is equal. So now you can take any slice of this thing, and you're going to have the moment on that side equal the moment on that side. And again, why this is smiley-faced, I guess my methodology is saying that, hey, look at these arrows. They're crunching in this spring, and then that means that this is really loose. So this whole thing is going to look like that, smiley faced. All right, so that covers pure bending moment. I think those are the two things that are helping me not make huge mistakes of trying to figure out, just by observation, if they're shear. Just because you have a downward slope in a beam does not mean that you have positive shear. You could have no shear. Shear could be 0 if you have this pure bending going on and you don't have any forces in the beam. So that is funny. You still have to have like a car driving over the beam to induce a shear. And there could be special cases where you do kind of have that wrench scenario where you get pure bending. But like I said, from a practical perspective, is the beam would have to have no weight. Because even if the beam has weight, that's the same thing as parking at least one car in the middle. So you are going to generate shear. So heck yeah. So again, I don't know if this style is worthwhile. You know what I mean? Comment if you're just like, nah. But I think it is. It's just like, hey, I ran into a trap and I'm trying to work my way out of the trap. You know, that's the worst part about kind of math and engineering is just like, whoa, I think I'm assuming something wrong and I'm running with it. So I actually need to relearn, and that's where it's a struggle to be like, whoa, I took calculus to a high level, but just going back to the basics is just like, yeah, so that's going to be the hugest, like, I'm like, hey, exclamation mark, do not confuse taking the area under the curve and plotting it and then getting a graph where it looks like there's another area under the curve. Sure, but that's going to be a whole nother relationship. And could I even explain that? Yes, and it's just like, even just saying that, it's just like, hey, if I have an acceleration graph and I'm going to say this is 9.8, then I know that my velocity graph is going to have a positive slope. You know what I mean? Cool. And the slope is going to be 9.8. And then if I know that, and then what's the area under this curve? Well, I can say that's going to be position. And I can say, hey, the slope, holy Toledo, the slope of this line is going to be the little, is it the little areas under the curve? Because the area of this, holy Toledo, the area of this is these values. So the area of that chunk is that value right there. So then if I have this, the area of this triangle is going to be this value. It's going to be hardly anything at all. But now the area of a small triangle and a rectangle is going to be a little bit bigger of an area. So that's why we're going to have this x squared graph. You know what I mean? Because now you have this little triangle, but now you're adding a huge rectangle. I don't know if that was a good analogy, but it's just interesting how just talking through the basics of integration, I think these are helpful. You know what I mean? And stuff like this is cool because you might be 2 steps ahead of me, and then hell yeah, that's going to be a very useful video. It's just like, nah, I already see the relationship, and I don't think I'm saying anything that's too wrong except that last little thing. All right. So I think that fairly well does it, and we can kind of go back to our sign convention for sign convention for shear and moments. For the shear, car drives across the cantilever from left to right. Heck yeah, it's going to bend down, and then we're going to get positive shear. And again, shear has to be like a point load, and hopefully I'm saying that right. Any point load on a beam, cantilever or simply supported, or just the weight itself of the beam is going to cause some sort of shear. Only when you have perfect bending moment do you not create shear forces where you just have pure bending. And that's a fascinating concept. I'll have to see kind of what problems might like be related to pure bending where you wouldn't have any shear forces. Because I think that's a true statement. Even just the weight of the beam itself is basically a point load in the center of the beam. All right, and yeah. So I don't think that this was a very good video about really diving into the nitty-gritty of doing the free body diagrams. But that might be a good place to end the video, to do a couple. All right, so we're gonna do the simply supported beam, and we got rollers on this side, and we're gonna have a load in the middle. And so when we do this, we chop it out of outer space, and we see that we have a load in the middle. If this thing was floating in outer space, it'd be traveling this way. We know that it's not. We know that there is some forces that are supporting it here and here. We just don't know what they are. But we know there's two concepts. We can also pin this to outer space, and we know that it's not like rotating. And the cool thing is we can pin it anywhere. We can take a thumbtack and pin it there in outer space, and we know that it's not rotating around that point. And then so we're trying to find AY and BY over here. And we know that at least AY plus BY have to match that. Because in this direction, you know, if we just have P, it's going to be traveling this way and accelerating. And we don't see that. Visually, we don't see that. So we go back to F equals ma. We look at this side, the acceleration side. And visually, we see a stationary object. So that means that this is 0. Now you have to go over this side and do some observation. Well, you know that this has mass, and it's part of under the Earth. For this, we're just going to say the mass is negligible. Or we could say this load is the weight of the beam that's going to act right in the middle. But for most, the beam has a constant weight all the way across it. So we're just going to say the beam is negligible weight, but we're going to put a huge load in the middle of it. But yeah, we know that. We put a big car in the middle of it. And why do we know that there's a force there? Well, we know this relationship with gravity. We know that the force is due to g m1 m2 divided by r squared. And so that force is going to be, and this is these three things are the gravitational constant. It's basically just mg. So that's where that comes from. And well, that would be the weight of the beam itself. No, I was saying that's the weight of the car. So yeah, we're putting a big mass on it. Sorry, I got kind of confused. We're putting a big mass on the beam, and we're saying, well, why does that add weight? Well, it's because you have a huge Earth underneath you, and the weight of that car is being attracted to the center of the Earth due to the gravitation of the Earth. You know what I mean? That's 100% what weight is. We just hand wave it away that, yeah, cars are heavy, and they just have an intrinsic weight. Well, that's only because we're really close to the Earth. All right, so so this side is like, hey, you're still doing some observation, you know what I mean? And this side is observation, and then I'm just going to do a little textbook, because you have to figure out what the forces are. And I want to make videos more about this, but yeah, where you just like, hey, take a pause and talk about what forces there are. And for material mechanics, and I should have been explaining this the whole way, but I just ran into it, is heck yeah, you have gravitation. That's what makes bridges heavy. That's what makes cars heavy on the bridge. But then like let's say you do have this 1-inch bar of steel, and we do put a force on it. You know what I mean? And we max it out. It's going to have an area of 1, and I always do this example of 58,000. We can put 58,000 pounds on a 1-inch area. It's going to change in length by 2 millimeters. It's steel. So that's the scenario that we go with. But internally, this is saying that the steel molecules themselves, if we take a 1-inch sheet of steel molecules that are 1 atom thick, you know what I mean? And then on top of it is another sheet of steel molecules that are 1 atom in thickness. There's an attraction between those two layers. And then when you start pulling them apart with this force, and we're pulling it apart with 58,000 pounds on both sides of a layer of atoms 1 molecule thick. You know what I mean? And so this is just a representation of the whole layer, but just with those. That means, so we have that P force there and that P force there. Could I do this? Like, is this the magic of free body diagrams? I'm going to cut that atom out of outer space, stick it into outer space, and I've identified a force on this side of this atom. So I'm going to identify that this atom has a force of 58,000. I mean, this is the magic and the detriment of free body diagrams. I think I have a really good method of saying, hey, chop it out of outer space, identify a force, and guess what? Just assume that it's moving across the galaxy with an increasing velocity. It's going to go light speed if it just continues to have this force. But we don't see that. We make the observation that it's not moving. So, so where's the only other place that it can have a force? It doesn't have a force this direction or that direction, and even if it did, those don't help balance this force. You know what I mean? If we identified that it had a force that direction, well, cool. Now it's moving this way and that way, and then we would have to balance it with a force in that direction. But we have identified that it has a force in this direction. So just by observation, it has to have a force this way. And we're just going to call this S. And that's a good term to do it because it brings up the idea of what are the forces that are at play. So, and it's a foreshadow, but we have gravity. And then the next force is the strong force. And then the next force is the weak force. And I don't know if you would do it in this order. And then you have electromagnetic. And that's about it. Those are the 4 forces in the known universe that we might be interested in. You know what I mean? So just from that perspective, and these strong forces are going to be your nuclear. Oh, bummer. And I think I have this totally wrong. But yeah, just learning on the fly. I guess the force between these is, like, the strong force is like what holds protons to neutrons. Hell yeah. Good luck breaking those apart. You know what I mean? You need, and that's where just even just talking about the basics, helps you have a fundamental understanding of different subjects. Because, yeah, once you need, No. Okay, so there is. Like, if you just have, like, something just pop off, you know what I mean? Like due to decay. Decay is a weak force. You know what I mean? So if something's just popping off due to decay, that's going to be a weak force. But now I don't want to say wrong things. But I definitely know a proton and a neutron. To remove those is a strong force. But now when it comes to just 2 atoms of steel, you know what I mean? 2 atoms of iron together, they're kind of like little magnets. You know what I mean? They're not covalent bonds like salt. NaCl are kind of locked in place. But these are kind of like little magnets, magnetic attraction. But by definition, I apologize. I do not know if it's a strong or weak force. But I kind of looked these up, so I'm going to take a pause and actually give you the numbers on these. Hooray, hell yeah. I don't like to write notes because I like to talk through things and you don't want to read anything anyway. But gravity is a hella weak force. Electromagnetism is 10 to the 36 times greater than gravity. And the strong nuclear force is 100 times stronger than the electromagnetic force. And then the weak force is still 10 to the 25 stronger than gravity. So that's where it's just like, at the end of the day, I don't care if it's a strong force or weak force. But I swear from medals, the interaction was the van der Waals forces. And it's just like, this is stuff if you were a material mechanics major. I wasn't. I was kind of a civil and environmental. But I'm just fascinated with material mechanics. But yeah, the van der Waals forces, aren't those weak forces? But at the end of the day, weak is subjective. It's hella compared to gravity. So even though I put an S here, it might be a W. I just don't know whether, I'll just look it up and then instantly know. But that's how I learn things, you know what I mean? Say something where you're just like, ooh, I think I might be wrong on that, or I just don't know, you know what I mean? Physics is all about, you're just like, well, there's two doors, and I think I walked through one, but I got to a crossroads where I just, you know, it probably is the other door. And you know, I'll probably choose the wrong door every time, but then I'll look up my mistakes, and then we'll make habits to go through those right doors. All right, so but in essence, we did the free body diagram. We on that layer of atoms, obviously it's the whole surface of atoms, we identify a 58,000 pound force. So in between, what's pulling on this atom is another 58,000 pound force, and that is, and like I said, I don't know if it's the strong or the weak force, but the internal forces from the free body diagram are the same as the external forces applied on those atoms. So yeah, that's the cool thing, and I will definitely rattle that off once I for sure figure out whether it's the strong or weak force all the time, because now you can break down material mechanics as like, hell, you have a big earth underneath us, things are heavy, buildings are heavy, and we need to support that weight, but we need to do so with molecules that actually have forces between them that kind of make them rigid, and where you can't, when you pull them apart, hell yeah, it's hard to pull them apart. When you push them together, you know what I mean, they retain their rigidity until they slide past each other and break. Okay, so that was a good tangent. So now that we go back to our simply supported beam, we have a force in the middle. All right, heck yeah. So I threw a new battery in. We kind of cleaned it up. So we have that force on the beam. We chop it out of outer space. We know that we have forces pushing up, and you know, just by symmetry or tacking it and finding that. You know what I mean? This I mean, if we take the moments about this point, you know what I mean? This force times this distance L over 2 is gonna spin this thing this way. This force is gonna spin it the opposite way. So those balance, and they still have the same distance between them. So just from that relationship alone, we know that these two are equal. And then once we know that, hey, we have a force in this direction. This thing can't be traveling across the universe, so we know that we got to resist it with the same amount, P. So, you know, that's just P divided by 2. But just going over the simplest things and then kind of talking through those concepts in not too much of a complex way, but not just hand waving and being like, oh yeah, if I have a force here, it's just going to be half. And you should still do that too. That's how we get the relationship with, you know, where you have, hey, if the force is here, these are P divided by 2. But now if you have something that's twice as long, and then you have the force here, then we need to focus. So anyway, so what we're trying to do is find the sign conventions for the moment diagram. We want to take a chunk and say that if we do this to it, it's going to be a positive moment. We're gonna smiley face it, and then and also if we pull down on this side, the right side goes down. That's going to be positive shear. So all around, that's going to be positive, and then it has to be backed up with that. So then if we do the opposite, if we're trying to do a frowny face, do your moments first, because now we're kind of half the battle. But like I said, the moments don't have to relate to the shear. So we have this frowny face, because this is all crunched in, and then this is a looser spring. And then by convention, if we're trying to get the negative for moment and shear, we're going to pull up on this side. You know what I mean? And then you could think of it, hey, I'm going to drive a cantilever, I'm going to drive a car from right to left over this cantilever, is going to pull this side down. Cool, so that is going to be negative shear, and this is going to be negative moment. So positive, negative. So heck yeah. So I think anytime I do a moment diagram, I'm going to draw these little blocks, and you don't have to draw them like that. I would just draw square blocks, and then what makes it smile, what makes it frown, and then the car, just a big old army truck driving across a cantilever, and whoa, it's gonna bend this thing down into that shape. And if you drive it from right to left, it's gonna bend this cantilever down in that shape. All right, heck yeah. So now how do we identify those forces? So we use this concept of chopping things, out of outer space. We're gonna chop this side where we're not gonna have that force over there. We're just going to have this. So we're going to have this little chunk. It's floating in outer space. We identify that it's got a P divided by 2. And right here, you know what I mean? A lot of ways to do it. You don't even need to, add anything on this face. You could just be like, well, the only place that we can have forces, because we've observed that from here to there, you know what I mean, all around this thing, the only place by observation is a force right there. But the second you cut it out, then at this plane between these atoms, you're going to have your forces and moments. So you know what I mean? And so the correct thing to do is just once you cut something, you have to throw in your positive shear. That's going to be a car driving this way. That's going to be a positive shear. And then making it a smiley face is a positive moment. And then you just have to go back to your free body diagram and say, hey, if I have an upward force here, I need to balance it with a downward force, P divided by 2. And that's the same direction as this. So this does apply, and we'll get a positive shear on our moment diagram. And now we're inducing a torque this way. So if we pin this thing in outer space, it's going to spin that direction. But we know from observation that it's not moving or spinning, and so we're going to have a moment that way. And the way to figure out the moment is it's the magnitude of the couple, because we have the same force here as there, times the distance. And you know what I mean? And if that's confusing, tack it here and just know that this force applies a torque of P divided by 2 times this distance. And now, just to make this make sense, we're going to cut this all the way out up until this force, just right up to it. So we have the molecules that direction, and then the molecules of steel this direction, and right on those molecules we have that force. But we cut just on this side of that force. So we opened it up, but we don't have that force on these molecules. And so we know that this length is going to be L divided by 2. And so if this whole length is L divided by 2, because if I chopped it there, then these lengths are L divided by 4. And so basically what I'm just going over is proving that if you have force in a couple, it's just the force times the distance. Because even that, from the engineering perspective, is a shortcut. Is be like, well, what's the torque on this? We'll just pick one of the forces of the couple because they're the same, and then just multiply by the distance. But if you wanted to do that from the thumbtack analogy, you would tack it here, know that this force would be a P divided by 2 over an area of L divided by 4, and that's going to be negative. And then this one is also a negative. So we have another negative P divided by 2, L divided by 4. Well, this is the same thing as negative P divided by 2, L divided by 2. And we just have that force, P divided by 2 times the distance between them. And we know that it's in the negative direction. So cool. So we know that this is generating, let's get rid of that arrow and draw this again. We're going to draw it to the half length. We don't have a P here. We have this P divided by 2 up. And we know over here by sign convention that this is positive shear, and then this creates a smiley face for a positive moment. And these agree that if we have this force up, this has to be a force down, so that's going to be a positive on our shear graph. We know that this is spinning it this way, and so we need something that resists it that way. And over here is the only place that we can have this moment. So it is in the right direction, and that moment's going to be P divided by 2, this force times that distance of L divided by 2. So now we have a moment of PL divided by 4 at that point. Okay, hell yeah. And now we can just go to our shear graph and start plotting points. We already found some points, and we can do it. So we can go to our shear graph and say we have oh, well, I guess it's just at this point. At this point, we have a P divided by 2 for our shear. And at this point on our moment graph, and at this point at L divided by 2 on our moment graph, if this is L, we have a moment of PL divided by 4, and it's also positive up there. You know what I mean? So then you cut this out of outer space right to the very edge. And if we take that tiny little slice, we have an upward P divided by 2, and then we have the forces. So we have this downward V. That's going to be a positive shear, and then we have a positive moment. But sometimes this kind of gets confusing. Had I just done this and just say, hey, we got this upward P divided by 2, we know that this thing's not traveling that way. We cut open a face. That's the only other place we can have the force, and it's got to be equal. So we have that. So now you just don't have any clutter getting in the way. But we know that this is creating almost no moment. So the moment's 0. So that means that we just have no moment. It really doesn't matter whether it's positive or negative. But we could say it's creating a very tiny moment, and it's still downward. So if we have a downward moment, it's going to cause this thing to rotate that way. We need to counter it with a couple, rotating it the other way. So we are going to get a moment this direction, very, very small. So just a very, very tiny number. And then by convention, then you can go back to convention and say, okay, we have this P divided by 2 up. And if we do have a force down, that's going to be a positive shear. We do have that. Check on reality. And then if we do have a bending moment this way that creates a smiley face, heck yeah, then we know that's positive. And that's the direction of our moment. It's just super tiny, if not 0. So we know that over here we have a 0 moment, and then we know it's linear. So we go up to that point. And heck yeah. And let's at least, you know what I mean? I guess I don't mind going over this. So we're going to go over this one completely and finish the graph and take our time. You know what I mean? Definitely chiseling things out of outer space, finding the shear forces, finding the moments. It's the free body diagrams that are just like, you want to feel like you're rock solid. And from that perspective, taking any chunk of whatever's being built, cutting it, knowing that you're literally cutting it at outer space, putting it into deep space, and then seeing that it's not moving. And then knowing that, hey, we still observe some forces on it, so those have to be balanced. Great, then we induce like a spin on it, a torque. And so we have to balance that, you know what I mean, by maybe putting a moment here, if we cut it from this, if we cut it out of that little chunk. But if this side was our support, and we cut that, out of the whole thing, then we expose that side. That's the side that's going to have the moment. All right, so so now we're going to, and this is good, you know what I mean. Sometimes I just have to be okay with knowing that my MO is long videos and kind of slowing it down just a little bit. So what do we know so far? We know that the shear is going to be P divided by 2. Oh yeah. From this, we also found that shear force. Yeah, I guess I totally forgot about it. That shear force is also P divided by 2. So there's our shear. At that 0, the shear force is P divided by 2, and at this point it is 0 for the moment. So heck yeah. So for our shear and moment, we already know that this is for at least halfway until we get to our P. This is P divided by 2, and then this moment is PL divided by 4. Heck yeah. And just in general, a cantilever is very obvious that the moment here is PL. The max moment is PL. And And I guess it's in the negative direction. So let's analyze that. We opened up this face. We know that to make it smiley face is the positive bending moment. We know that if we drive our truck over this side of a cantilever, if we're opening that face, if this side goes down, that's going to be associated with the negative shear. You know what I mean? If we take the cantilever this way and drive over it, heck yeah, that's positive shear. So I was about to get it mixed up, but yeah, heck yeah. So, and then what do we observe? We observe that this thing is downward this way. So we're going to have the positive, you know what I mean? This whole thing is going to be, when you put the load there, it's going to be sloped that direction. And so that's synonymous with positive, which means we have a downward force and an upward force causing that. So this is V positive. So we expose this, so we have this upward V, and that's going to be positive. If we have the downward P, we have to balance it with an upward P, so we know that our shear diagram, at least at that point, is going to be P. And then for this scenario, it's going to be all the way across, because we could take, now you could just take this out of outer space. You have a P there. The only place that can have a P up is on that cut face. So there, I'm getting there faster, being like, hell yeah. Just chop it, keep chopping it, and then you'll just have that P all the way across. But the moment over here, this P equal to that P up causes a moment of PL in the downward. So the only thing that will actually balance it is a moment this way, and then so our actual moment due to the free body diagram will be that way PL. But by convention, this is what we call positive bending moment for our graph. We have it the opposite. So we know that we're going to get a negative P divided by L for our graph. So when we go, this is the shear, and then when we go to the moment, we're going to have a negative PL over there, and then just by getting right to this real far extreme, if we take that little chunk P this direction, balanced with a P that direction on the cut face, very tiny moment. This distance is super tiny, so we do have a negative moment, and then we have to couple it with a moment this way, which is a positive from the free body diagram perspective. But again, if we do have this up P. If we say that we go back to this, if we have an upward shear, that's positive. But then if we have something that smiley faces, that's positive. What we find is we have the opposite of the smiley face. So we still have a negative moment, but it's just real tiny because this thing is hardly spinning. These forces are almost in line. So it comes in negative and it hits right there. So then that's enough information to be like, hell yeah, that's the moment diagram. It's below here, but the slope of this line is positive, which says that heck yeah, you have a positive P for our shear. So positive shear, but a negative moment over here. But it makes sense because it's the area of this graph is holy hell, yeah, the area under the curve. So hey, right here, there's no area under the curve. So that's that point right there. Oh, so this would be the would this be the scenario where if this was, let's work at this, because if this is how does this work out? If this is the equation for a line, y is equal to PL. Okay, and then we're going to integrate it. And we're going to say, I'm sorry, holy Toledo, this is just P. So we're saying y is equal to P. And this is enough mathematically to make my head spin to be like, no. Even calling it y is confusing. Well, we're saying the shear force at this point is P. So we have the shear force is equal to P. And it's P at all points. You know what I mean? If you mistakenly threw an X in here, well, at X is 0, you'd have the shear as 0. We don't get that. We just have a constant line. So even the most basic, equations can sometimes be the most complex. All right, heck yeah. So yeah, we have an equation for shear. It says shear is equal to P. It's a constant. It's a straight line. And now we want to integrate this to find moment. So we're gonna say moment is equal to Px plus C. And when we have an x value of 0, hell yeah. So this is the first time where we do get a constant of integration. Because when we throw in 0, so our length is 0 to L. When we throw in, this is x, this is the origin, this is positive x. When we throw in a value of x, our moment is negative PL. So we got negative PL is equal to P times 0 plus C. So now we know that our constant of integration is negative PL. So finally we have an equation for this line, and its moment is equal to Px, which makes sense because we have a slope, and the slope of this line is the shear. You know, especially if it's constant, it is just that value of shear at that point. And so heck yeah, you have a slope of P. You know what I mean? And you always have a slope of P. And then where it crosses the y, if this is the y-axis, heck yeah, it crosses the y at negative PL. So our equation is this slope P. So, you know, equation of a line is y is equal to mx plus b. So P is the slope, and b of negative PL is where it crosses that y-axis. Heck yeah. So now we have an equation for moment. And now we can say that yeah, and I guess I'm just going to go back to kind of what I know. I'm going to say, hey, the area under this curve is the area under this curve right here. Holy Toledo! I guess you still need a starting point. You know what I mean? So at x is equal to 0, the moment is negative PL. So I'm already over here. You know, and then integration says as I walk along this, I have this area right here. I'm going to take one step. You know what I mean? And so the steps are the slope. Hell yeah. So I took a step, and then we're going to take another step. And at every part of this, the areas are the same. So I'm just taking constant steps. If at some point this got twice as high, well then my steps would be like, whoa, I'm still going this way the same amount, but now I'm going down like twice, you know what I mean? And so now my slope doubles. And so that's what that means. So this height, this area is the slope. And if I just go this direction, 1, slope is the rise over run. And if I just say, hey, I'm just going to go over 1, well, heck yeah, I go up the slope. So, heck yeah. So that's going to be very useful for me. But, man, and I'm sure other people, you go through calculus at a high level, but then you just come back to be like, what? Like, you know what I mean? What's the basics of integration? And it's no joke. I mean, that's why it's just like, what's that good book? Change is the only constant. Books like that are just $1 million books. And it's $1 million concept to just go over the basics. Talk about something at a high level, but then be like, whoa, guess what? We probably all forgot the basics of differentiation and integration. And it's just, it makes you feel dumb. It's like, I just remember in middle school, it was such a cool moment when the teacher was like, you guys don't know your times tables. And then we kind of just like laughed, be like, haha, of course we do. And we don't. We didn't know them to a high level, and we couldn't spit them out. And it just seemed childish to review times tables. But then after we literally did times tables for 2 to 3 weeks until we just nailed it. And it was like, that's what I remember from middle school. Like that's a middle school math moment that I'll cherish, because it's allowing yourself to go back to the basics and to be like, yep, I bet you you can take a lot of baby steps that will really help you accelerate when you go back to the complex analysis. All right, heck yeah. So now the next part of this, we got that part of the graph. The next part of this is to cut this out of outer space. And guess what? We're just going to go right to this point. And we're going to definitely do it two ways, because you could also just cut this section out. We already know that these are p divided by 2, p divided by 2. So let's do this one first. So we have this L over 2. We have a p divided by 2 and a p right here. So we're going to try to figure out the easiest ways, and we expose this face. So let's do it 100%. And this is the downward shear. The car drives across and it causes that type of motion. I got it. And then a smiley face, trying to make this thing look like that, is a positive bending moment. And just in general, that's what we're seeing, so that's what we should expect. But then the shear is probably the hardest thing. That's why the moment you should start with first, but it's like, who knows about the shear? And we already proved, again, if you have pure moment, this bizarre. There is no shear force. Cool. So now the forces have to balance. So we have this p down and half up. So just not even, see, that's why this stuff gets in the way. Because just from this perspective, we must have an upward force of p divided by 2. This is p divided by 2. And guess what? This is in the wrong direction. So now that we know that for our shear diagram, we have to have a negative p divided by 2 for our shear diagram. And then even on this, it still works out. This is a free body force, that's just in the wrong direction for a free body diagram. So if we just said this is point B, and we just thought by was in that direction, well, it's not. It's negative p divided by 2. So from the free body diagram, everything checks out. From the shear perspective, everything checks out, because this arrow is up. And then so when we go to sum the forces in the y is equal to 0, we're going to say negative p down plus p divided by 2 up. And then we're going to say this is down. So we're going to say minus, but this is a negative value, minus negative p divided by 2. So a lot of ways to get this back to positive. So now we have negative p plus half a p plus half a p. And we're just good to go on our forces in the y. But when we go back to our shear diagram, this is going to be a negative p divided by 2. And foreshadow, on this side we had positive p divided by 2. So after we cross that molecule, hey, we have a negative p divided by 2, and we'll probably assume all the way across now. But we'll definitely take the free body diagram all the way over here. And then what's the moment? The moment's probably a little bit trickier. So now right here we have obviously, it gets confusing with the sign convention. All right, hell yeah. So my camera overheated. We had to take a little break. And, you know what I mean? What are we doing? Well, we're trying to find this side of the force and kind of what's going on. And so I think where we left off was it's just, it's kind of better just to kind of forget about this stuff at some point. And we have this p down, p divided by 2 to balance. We know we have to have a p divided by 2 in this direction, just to balance the forces. And now we have to figure the torques on this, So let's just do the pin at this point. There's more forces over here. So if you tack it into outer space over here, and then we're going to see, that this force actually makes it spin, But from observation, we know that this thing is not traveling in any direction and it's not rotating. And so if we have this torque, which is, this is L divided by 2, so now we have a torque of, in this direction, p divided by 2 times L divided by 2. So we have to balance it with a moment this way. So sometimes just doing the free body diagrams, we have a force up and a moment this way of p divided by 2, L divided by 2, PL divided by 4. Okay, cool. So now we need to figure out, is this going to be, so this moment's going to make it smiley face, so that's really easy to see. So we know that's a positive moment. We know this force is up, so by sign convention, on this right side, if we drive a car over a cantilever, it's going to be that way, and we know this is positive. So if this went down, that would be positive. This is going up, though. So we know that by convention, this is a negative shear of, or a shear of negative p divided by 2. You know what I mean? So then on our graph, we're going to go down, and so this PL divided by 4 is that moment, but this shear is a negative P divided by 2. Sorry, the graphs are getting a little bit together. But the moment's still positive. The moment's still positive PL divided by 4. It's up there. And then the question I was asking is like, well, wouldn't it just have been easier just to chop it this way and find out what's going on? And by convention, wouldn't everything be the same? So we're going to chop that side out. We can go a little faster. We have P divided by 2. It's obviously not traveling that way. We have P divided by 2 again. And why is it over on this face? Because we just by observation, we observe that there is no force all along here, and all along here. So the second we chop it, that's the only place that you can have a force. And from a more advanced level is like, heck yeah, if you have something, you know what I mean? Well, like this, and then you're going to chop this, and then you know basically out of the wall, and who knows what this direction is? It could be a three-dimensional object, and this force is going to be at some oblique angle in the X, Y, and Z direction. You know what I mean? And then so if we chop that out, and we do something like this, you know, we expose the face, and we go back to our convention of, you know, if we drive the car on this right to left side, it's going to go like this, and that's going to be a negative shear. So it's that is going to be a negative. So a positive shear will be in that direction, and then the moment will be in this direction. But we're in 3 dimensions. You could have, I mean, this is a vector and this is a vector. You know what I mean? Your shear could be well, your shear, if this face is normal to that direction, your shear could be you know, coming out at us, out of the page, or any other, you know what I mean? So obviously the shear is in that direction. So when we chop out something, we have a normal force, and then we have a shear force, and then we have a moment. But the moments can be, you know, in 3 dimensions. It can be in the X, Y, Z. The normal force, well, I guess is going to be in the direction of this. But if our X, Y, and Z is at some oblique angle, this normal force has a component in all directions, X, Y, and Z. You know what I mean? The shear can have components in X, Y, and Z. And then the moment doesn't have to rotate about some symmetric, you know, looking picture. The moment can be rotating around some oblique, and I don't even know if I'm using the word oblique right, but anyway, just some sort of vector in the X, Y, and Z. So therefore, you know what I mean, you could have a moment in the X, a moment in the Y, and a moment in the Z. The normal force could have a normal component in the X, a normal component in the Y, a normal component in the Z, and then the shear force could have a component in the X, component in the Y, component in the Z. So just kind of at an advanced level, you know, I mean, that's where, you know, vector geometry, you know, an analysis would take you. So just know that from that perspective. All right, so back to what we're doing. We chopped it out just to this side of this force. So molecule for molecule, this P was over here, but it's not in our free body diagram. We chop it out just before those molecules that are acting on that. And so now we're inducing a force. This is L divided by 2. We have a torque that way. Again, let's go back to here. Like, we don't observe any forces on here because it's just free. There's air all the way around here. But then the second we cut over here, heck yeah, this is where we're going to have our moment and our shear. So we balanced it with that force on our shear, and now we balance it with the moment. So these two create a couple of P divided by 2, L divided by 2 in that direction. And so we need to couple it with a moment in this direction of that force, P over 2 L divided by 2, which is PL divided by 4. And just by convention, this is in the positive direction, and then by convention, this force is down over here. If we drive our car across that way, well, again, that's going to be a negative force. And so, yeah, we get to do it equal and opposite. Because when we took the diagram of this, we chopped that out, and we found that this force is up over here. And if you drove a car across a cantilever this way, it would bend down. That's going to be the positive. But we find which is synonymous with this force down, but we find a force up. So we find the opposite, so that must be a negative shear. So that's going to be the trick that I use. You know what I mean? Have a Army Jeep drive over a cantilever and see how this bends from left to right. That's going to indicate positive, and if you do the cantilever with the car going right to left, it's going to bend it down that way and negative. I don't know. I just think it's a good way to analyze that. All right, heck yeah. So now we have just on this side of that point, like what we got. We got a P divided by moment's the same, PL divided by 4, but the shear is just drastically opposite. You know what I mean? So that's that. And then we would take a free body diagram right here. So you can either take this tiny slice, and I guess we're just going to go real small on our picture. So we have a P divided by 2. We're going to balance it with this, P divided by 2. It creates a torque that way, but hardly at all. We're going to balance it with a torque this way that's almost close to 0, but it's just not. It's real tiny that way. Again, this is a smiley facing moment, so now we're doing pretty good. So our moment's going to be just slightly positive at that point, and then approaching 0. So then that covers that. Our shear is down, and like I said, I take a pause. There's no way I'm going to get good at just automatically knowing what this means. So if I'm on this face, and that's the cut face, I'm like, hey, that's the cut face. So let's the other side bolt it to a cantilever wall, drive a Jeep over it. And then this is indicating a negative shear if we're going to go right to left. And that's what we find. It looks like we have a downward force, and then they match. So we're going to have a negative P divided by 2 right here. So negative P divided by 2. And hell yeah, we completed our shear diagram and our moment diagram. But the other way to get this moment over here is to chop. So this is going to be a good check on reality when I do actual harder moment problems. Because now I can cut wherever I want. I'm going to cut all of that, and I'm going to say right here, I'm going to have those molecules with the P divided by 2, but I'm going to just cut on these molecules. So I basically have the total length, but right here, these molecules don't have this upward force on them. And I cut it out of space, and so I guess I'm just going to draw it right there. Full length, we have P in the middle, P divided by 2, so that means over here to balance, we must have an upward P divided by 2. And look at this, this is full length now, so literally there's no moment, you know what I mean, it is balanced moment-wise, so I just know the moment's 0. And that's what we get. We get a moment of 0, this upward face. Like I said, I have no idea how to do the sign convention, but I opened up this face over there, so let's bolt that side to the wall with a cantilever, drive a Jeep over it. This is going to bend down. We're going from left to right. That's going to be a positive sign convention with a downward force. What do we see? We see an upward force. You know what I mean? So hell yeah, that's going to be synonymous with a negative P divided by 2, and that's what we see. So that's kind of cool how you can cut from the left or you can cut from the right, and it's where you do the slice it is going to be your value for that and the value for that. Now that's all the information you're going to get. And just by observation, then you can make straight lines. But some things, I mean, man, you're going to have that this beam has mass. So every little section, you know, has a mass and a little mg. You know what I mean? We'll just call it m prime g. So I mean, it's just like having a force right there, and then you know, so all those apply, and so that's going to drastically change the free body diagram. So you could, that's why you could take multiple slices and kind of feel what's going on. You know what I mean? So then your shear is going to be, hey, it's going to be sloping. And then if we're saying that this moment is the slope of the moment diagram. How do we say this? The slope of the moment diagram. Oh man, get some more light. Heck yeah, we are gonna take. We're gonna figure this out, because that's why you go back to the basics of, hey, if we have what were we even saying? The area under this curve is basically the force times this distance. Well, that's going to cause a moment. You know what I mean? So that makes sense. A force times a distance, P divided by D, that's going to cause a little bit of moment. So then we're just on this moment line. And if this is like this, well, heck yeah, this area is small. So then just from that, the area is small, gets bigger. You know, that's going to be synonymous with this. Hey, we have a small area, we're not really changing very much, but now we're taking bigger chunks. So back to calculus is like, hey, let's say we have 1, 2, 3, 4, 5 steps, all of equal steps, and we're doing 1, 2, 3, 4, 5. 5 equal steps, and we say, hey, the area of this is... and then I guess we got to go down to 0, because if we're right here, there is no area. Once we take the first step, we calculate that area, and then we pop up just a little bit. Sorry about this graph. And then when we take another step, heck yeah, we kind of pop up a little bit more. And then, you know, it's not just a linear. If it was a linear line, we'd be like that, but we actually popped up a little bit more. And you know, even from here to here, if it was a linear line, we'd be like right there. But the next one, hey, we have more area. You know, we pop up a little bit more. And even from there to there, if that was a linear line, you'd just be going along there. But no, we take another step and we even have more area. So it's always just going to be a little bit higher. So heck yeah, so it's going to be a little higher than that. And that's a good analogy of knowing the x squared graph. You know what I mean? And for the most part, that's about all you need to know. You need to know the integration of a constant line, and then integration of a sloped line, and how that creates the equation for an x squared. All right, so man, I think I'm pretty good. I'm gonna pause the camera and see if we want. Well, let's just do one more to finish off. I mean, these are the basics, and it's just wild to spend, you know, too long on the most simplest ones. But we're going to do a cantilever from this side just to do it. So if we cut it out from outer space, we have a force here. Here's where we cut. We know that we have to have the same force up. We're going to cause a moment this way, so we're going to have to do a negative moment that way. Here's the only cut face that we can put that negative moment on. And the moment is going to be PL, because this caused a couple times the distance is that moment. So hell yeah, now we're on a roll. Now by sign convention, well, here's our cut face, and then chop it to that wall. Drive the Jeep across it, heck yeah, that's going to be a positive bending moment. We're driving the Jeep from left to right. And this would be a force down, a force up. So on our side, we see a force up. We see opposite of this. So we're going to have on our shear, and we just know one point. On our shear, we're going to have a negative P. Then we go to our moment diagram, and we saw that we have, you know, this is going to make a smiley face. If we had two of those, if we had, you know, something like this, and we did a moment there and a moment there, well, it's going to bend it, it's going to shrink up this real tight with the spring, and then loosen this side. So now you're going to loosen that side, shrink that side, you know, tight spring, loose spring, and now we know that that's going to be a smiley, a frowny face moment. It's a negative moment. Cool. So now we're on a roll. We know we have a negative moment of, and where do we want to do this? I guess just right here. So our diagram. And we have a negative moment of PL. And yeah, we're going to do these both ways, because this is where I ran into, like, if you do the cantilever from this side, heck yeah, you have a negative shear mashed up with a negative moment, and it just seems like it makes sense. It just seems like, well, if you have the area under the curve, you have like negative area. I don't know. It just, but that's not the case. That was the trap that I fell into. So we're going to talk about that trap just in a second. All right, booyah. But now we need to figure out, other places to take the moment. And so we're going to, hey, we already found over here. And sometimes this is the more complicated one to do. Well, let's chop out half, even though we don't need to. We chop all the way to those molecules, but maybe we don't know to do that. So now we just have that left half, and now we're going to say, we're going to say that we have this moment and then this force P. You know what I mean? So we have a moment of PL and a force P. How do we balance? This is our cut face. We have to balance that, these P's balance, so we know it's not traveling this way or that way. We have a moment this way, so it's going to make it spin that way. So we need to put a moment this way to keep it from spinning. And that moment's going to be PL. Oh, okay. That moment's going to be PL. And then by convention, this is the only way that I'm going to figure this out, so I'm just going to hammer it home. This is our cut face. Draw a cantilever, drive a Jeep across it. Heck yeah, we're going to shear it that way. If we drive a Jeep from the right to the left, it's going to be negative. And so that's going to be this force up, this force up, this force down. What do we see? We see a downward force. Cool. So we're going to have a positive shear. It's going to indicate positive shear on our graph. We're going to have a positive shear of P. Whoa. Did I do that wrong? I don't think so. But where's the discrepancy here? Oh, no, okay. No. Did I do this wrong? Let's say we ran into a hiccup there. And so let's just cut. Let's go to the other half. You know what I mean? And, so that's the cool thing about free body diagrams. You have two ways to maybe catch your mistakes. So we have this P down for sure. We opened up this face. We must have a P up, and this is causing a moment. That's the deal. Okay, sweet. So I know what happened over here, so let's go back to this. Or do I? Yeah, no. I know what... Oh, dang it. Maybe not. I think we need to go over here. So if I go to the halfway point, this moment that it's causing this is L divided by 2. So I know I have like a rotation of this. If this was just floating in outer space and I put this couple on, it would be spinning like that. And it would have a torque of P L divided by 2 that way. This is my cut face. So I need to balance it with a moment that way of PL divided by 2 at the halfway mark. Cool. And so at the halfway mark, I have a downward moment, which is a negative moment, of PL divided by 2. Cool, so it looks like we're trending, it looks like that's going to be our moment diagram. But now what is our shear? The balancing force is going to be up. So maybe I just messed up from the get-go. And yeah, that's probably what happened. I said, so let's go back to here. Let's see if we caught our mistake. I chopped this out of space. This is my cut edge. I say that I have an upward force, a downward moment, and then so if this is my cut face, I mount it to this wall, drive a truck over it from this side. I think that's where I messed up. You know what I mean? Drive a truck over it from that side. We're going to have this, and we're going to have a positive shear. So I'm glad I caught my mistake on there. So we have a downward force and then an upward force to do that. What we see on the cut face is an upward force. So we know we're going to have a negative shear. So we're going to have a shear that's going to be negative P. So, and that's what we do. That's what we have right there. Is that right? Yep, because I mean this thing, if we have a P on it, it's gonna look like that, and then that looks like we drove a car over it from right to left, which is the negative convention for shear. Okay, so this equation is slope down, you know what I mean? So if we take the slope of this, if we go a distance 1, we're actually going down negative P. You know what I mean? So we know that the slope of this line is down. So I'm just confused where I'm running into the issue with chopping it out on the other side. That's why I'm doing these videos, to see like where are the mistakes that I might make for the more complicated problems. So now what I'm going to do, just molecule for molecule, I'm just going to chop it out from over here. I know that this side has to have P up. So we know what this side is. These molecules right here have P on it, but these don't. And so now I have a cut face. I know I have to have a downward force. I know my moment is going to be this direction with the magnitude of PL. And so I need to couple it with the moment this way. Now is that right? So we have a torque this way. I need to couple it with the moment that way. Holy Toledo. So is one of the aspects of doing moment diagrams is that you can't sum from both directions? I have to grab a new sheet of paper because we're gonna solve this. Holy Toledo. All right, so we have the cantilever, we have L, and we're just going to chop it out of space. We have to have a force here. We open the force there. And then this is going to cause a rotation that way. We need to balance it with a moment that way. Moment's negative PL. I mean, this moment is just PL. But by convention, the moment, by convention, is a negative moment of PL. So it's in the negative direction. And then the shear force is up on the right side, and and this is going to bend like this. So it's up on the right side, which is a negative convention for shear. So shear over here is going to be negative P, which we had, and then the moment is going to be negative PL over there by convention. And then so what I wanted to do was take out a slice right here of hardly any thickness. We still have the P that way. We opened up this slice, so we have to have a P downward. But these two cause literally no moment, but we still have this moment in this direction of PL that way. So we need to counter it with a moment this way. All right, hell yeah. So on this face we have a moment of PL this way. Now by convention, this is causing a frowning. You know what I mean? So if we take this and put a moment that way and a moment that way, shrinking there, lengthening there, and we get a frowning. So heck yeah. So this moment by convention is a negative PL right there. So that corresponds with this negative PL for moment. And now this force on this side, this is where I was getting the hiccup, and let's see if we don't get the hiccup again. So we're going to have a downward force over there. It's going to cause that type of shear. This is synonymous with a car driving across the bridge this way, which is synonymous with a negative. This value we just know is P, but it's synonymous with a negative moment. Heck yeah. So that applies right there. So now, so that all worked out, and we did it, and I felt like we did it both ways. Of taking this, chopping this all out and finding it there, and then chopping it this way and finding it there. And that's what got me confused from over here, and now I think I caught my error. Because now if we already chop this out, we know we have a P down, a P up, but we also have this moment, PL. So now if we want to chop from this side to over here and expose that face, I think that's where we ran into the issue. We can do that, but hey, we still observe these moments. and that force, so we have to have the downward force. Alright, heck yeah. So on this cut face, this new cut face, we have to have a downward force, and if we have, so now we have a lot going on here, because we have this moment of PL. This couple produces a torque this way of PL, kind of in this counterclockwise, what we would call positive direction. This creates a PL that way. So these cancel. So this moment over here is just zero. So we have no moment over there, and that's what we'd expect. We have this shear force down. That's going to make something like this, which is synonymous with driving a car over a cantilever this way, making this shape, which is down, right to left. And then so if we have a force down, that's a negative convention. Force up right here is also a negative convention. We observe that these match. We have a force down and a force down with a negative convention. So right here we have the negative P. So heck yeah. So at least we're back on track and we caught our mistake, and yeah, we did it. So I guess the only other thing to do is right off the bat, let's just cut this out of outer space right there, and we're going to say, hey, these molecules and these molecules, this has the P on it. We're just going to chop those tiny molecules out. When we do that, we get this small slice. We have a P on that side. We have to balance it on this cut face of a P on this side. It really creates no tension. If it did create a tension on this, it would be just slightly, just be slightly positive. It would be slightly that way. But just super tiny number that direction. So on this, holy Toledo, I apologize. So this moment just in general creates a torque that way. This cut face is the only thing that can resist it, so we would have a moment this way to resist that torque. And like I said, this moment is just a really tiny number. By convention, on something, a moment on this side and a moment on that side, really crunching this up and lengthening this creates a frowny face. So heck yeah, this arrow starts to crunch in these molecules. So that's a good way that I can visually, even if I just have one moment on one side, I can see that these arrows crunch, and then this arrow is kind of stretching these molecules. So heck yeah, we have a downward smiley face and almost of zero. But we still, if we're taking just right out there, just a little bit over here, we definitely still have a negative convention moment. A downward smiley face is a frowny face. So we definitely have a frowny face, and it's right there, and we can just see that this, approaches zero. So that's a check on reality over here. Now for our shear, well, let's see if that's a check. And now I'm getting used to it. I see that it's an upward force. It's going to take that thing and look like that, which is synonymous. If I have this shape, like I'm not driving a car from this side to there. You know what I mean? So obviously I'm driving a car across something that looks like this, and we're inducing that shape. So that's indicative of a negative shear. That's going to be a force down and a force up. So what do we witness on the face that we're cutting out? Because again, there is just air molecules surrounding this side and underneath and just to the right of this force. The only force is acting right on those molecules right at the top. But when we cut this out of outer space, the only place that we can have a shear force, a normal force, and a moment is right on that face. There's no other place to have it. And so that shear is going to be up, and it's going to be on that face, and it's synonymous with this upward, and that's a negative convention. So right there is also a negative P. So heck yeah. So I think I have enough basic understanding of sign convention now, but I would not want to apply it to any more complex problems than just a simple beam with a force in the middle and a cantilever with a force at the end, and then take as many free body diagram chunks. That's where, as an engineer, people just aren't, you know, like it's a magic trick to take the free body diagram at the place that makes the most sense right off the bat. You know what I mean? It's going to help your development if you have the confidence to take a free body diagram right at those first molecules, that first stack of molecules, and say, hell yeah, that's my cut face. I know that there's a force on these molecules. You know, so just to the right of them, it has to be a balancing force up on that face. It's causing a torque this way. So we would see rotation if this thing was in deep space, but we don't. So we know that on this face, we have a moment that way. We know that by convention, it's crunching, it's stretching. We're going to have a frowny face. So we know even just one molecule to the right, we're going to have a tiny moment, and it's going to be a downward, a frowny face convention, just a slightly negative. And then right here we have an upward force for our shear that's equal to P, and that's going to cause a shape like this. How are you going to drive over it? Well, it looks like you drove over this way, and so if we drive from right to left, that's a pretty good convention. That right to left is a negative. If you drive a Jeep from left to right over cantilever, that's going to be a positive convention. And to get this shape, you must have pushed down and you must have pushed up. And what side are we? We're on the right side, and we have an upward force P with an upward shear. So those are synonymous. Those look alike. And that's a negative convention. So therefore, negative P is our value there. And we just analyzed one point. But yeah, so this is going to be excellent going forward to do complex problems. Because I don't mind just choosing any point and analyzing it, getting a number, and hell yeah, at least I got a number for the shear and the magnitude. Even if it's doing like wildly, you know, crazy shapes for the moment and wildly crazy shapes for the shear, it doesn't matter. I can have now a high level of confidence that I can find at least one moment at a point and one shear at a point based on this convention. And that's the take-home point of calculus, is just like, cool, it's a magic trick to know how calculus works to get that full, you know, crazy equation for everything. It's engineering just to be like, who cares, and find one point, maybe the midpoint, and be like, hey, that's probably good enough for the answer that I'm trying to find. And just to get the general gist of the problem. Because at the end of the day, this max moment is what's, you know, your maxes are what you're interested in. So if you can, you know, find any point, you know, you're more than likely going to find the actual point or like the halfway point. So your answer, even just by analyzing one aspect of a free body diagram, will get you pretty close to the answer that you might want. So that's taking calculus and then putting it into a practical application, you know, of not doing the magic trick and finding those magic points where you think the moment is the maximum. You know what I mean? Stuff like that. And where the shear is the minimum. Because on a cantilever, yeah, it might not. You'd be like, hey, where's the shear the most? You know what I mean? That's a trick question. That shouldn't be asked. I absolutely despise the physics books that are just like, hey, you know, could it be A or could it be B? You know, you choose. That's a horrible way to learn physics because I don't know. You know what I mean? You obviously asked a question and it seems like most people don't know, and then you have to rely on some sort of bizarre intuitive nature. I don't know. I got complimented in a fluids mechanics class because I would just be eager to guess, but I would kind of guess wrong. But the professor gave me some sort of weird compliment, like, oh yeah, David's got some sort of intuition. And it's just like, nah, like I'm always going to guess wrong, but I guess I'm at least going to be able to guess. So that's my strong suit. It's just like, I don't mind guessing wrong and then seeing the right answer and then figuring out a way to change my brain and habits to understand from the fundamental perspective, why couldn't I have got there faster? You know what I mean? And so that's what I think I can provide in my long format videos. And I think, alright, unless I need an addendum to this video, I'm going to end with at least, you know, throwing up the sign convention Heck yeah. So here's the sign convention. You know what I mean? At the end of the video, if you want to pause and read through it. And then I'll also put the other part of this literature. Alright, so here's the other part of the text on sign convention. And I just want to talk about, my style is not to read text. I'm kind of ADHD, where the second I start to read a sentence, I just lose my mind. Especially when it's physics and math. I always, like some strategies, I always just go to the question. And then I just look for the numbers. You know what I mean? Like, oh, okay, the area, the length. Because it's too much to, like my comprehension, you know, is kind of wandering. And so, but what I'm going to do after doing this video is I'm going to read these two portions of text. I'm going to read the sign convention, and then I'm going to read, you know, this whole text all the way through. And from that perspective, like using an equation, throwing it at it, and then doing a bunch of problems, and then going back and reading the text, it's very bizarre. It's like taking statics and dynamics and then opening the first page of like statics and dynamics, you know, talks about how we're using F equals ma, and that's a Newtonian philosophy, and it works for masses, you know, considering all mass like kind of like point masses, but that's going to break down at the quantum level. And it's just like, just reading text is so fascinating from that perspective after you already know how things work, because those just set in like concrete. You're like, whoa, like never really realized that. So like material mechanics, we're in the realm of observing that things have mass, and that we know that there's this relationship between force and mass times acceleration. That's the world we live in. And then just the take-home point, like kind of just reading text after doing the equations. You know what I mean? Things will just pop out that you just obviously would glance over on the first time reading. So I'm seriously, after I end this video, I'm gonna read through here, and maybe even come back and see if I came up with something mind-blowing. I can't imagine just for this sign convention, but because I think we basically covered it with the integration, basic integration, getting equations, shear and moment, and figuring out the sign convention, Jeeps driving from right or left, you know, I mean, positive, negative, smiley face, or frowny face for the moments. That's the take-home points. And I think we got sign convention down. So thanks for joining me. And hell yeah, thanks for joining me through like how anyone would learn. You're like, hey, I don't know it that well. So it's like, I remember skateboarding. It's like, if you're learning how to ollie, you do not throw out your money to watch a professional ollie in front of you 1,000 times. It's not going to help your ollie. You go to someone who's hella struggling, but can still just ollie just a little bit. Someone that looks like you, and then someone that's just a little bit better than that person. And be like, whoa, what can I change from the person that looks like me to the person that's just slightly better? And so that's why even doing this videos, just having glaring, and I'll have to throw a disclaimer at the beginning, just because even just having errors just right off the bat, that's the learning process. And I like this format where even the listener, you might be 2 steps ahead of me, and that's a cool process. That means you're actually learning. And then just the having someone constantly talk, where you could even listen to this as a podcast, potentially not really, you probably still have to watch it. But that's kind of my goals with videos, is like, hey, could you just have a streaming conversation where I could just talk about a subject, and you could have it running as a podcast where you're like, okay, I get it, where you really don't have to look at anything visual. I think that's a fascinating concept that I would like to explore. But heck yeah, and just that aspect of, you being 2 steps ahead. Now definitely, some of these, my style could be a little bit messy, where you're just like, nah, I'm kind of lost. But I don't think so, because I keep repeating, we go back. That's the thing that's not on YouTube. That's the thing that right off the bat, that is definitely an MO for like, whoa, over explanation, going back to the basics. I mean, that's what we did. We would basically relearn simple integration, and I learned more today about integration and differentiation. And again, it's such a, like, I'm going to forget that. I'm going to have to come back just Just always, you know what I mean? And just learning that any equation is a relationship between two things. So when you have a y is equal to an x, well, those could be two, they could be anything. And then when you integrate, you are basically saying that, what are you saying? Holy, I don't even want to get into it. But yeah, you definitely have, the moment is a force, times a length. The shear is just a force, you know what I mean? So it looks like you took the force times the length, you took whatever that shear was over a little bit of length to get, you know what I mean, the moment. But yeah, it just needs constant grinding in, just even that basic integration. So there's the take-home point there. Anyway, hell yeah, thanks for joining me, and guess what? That's a video. All right, hell yeah. So I just read it. We're going to do a little addendum. You know what I mean? One last push of kind of what they want. Now, this first part talks about these diagrams. And what it says is like, hey, if we're on this right side, this is the convention for positive moment and positive shear. Get used to it. You know what I mean? And, like, back to the free body diagram, if we do have like point A and point B, well, we're just going to assume that at point A we have an AY up and then a BY up. You know what I mean? Because those are the positive directions. We're saying this is positive Y and this is positive X. And but over on this side, we're having a downward force. So even if we did chop this section out, so we'll chop it out, you know, by convention, we would say, hey, we have some sort of P up, and then we're just going to say, hey, we have some sort of force over here, and maybe it's BY. We just don't know what it is. So from a free body diagram perspective, this is what we're going to say. And then if we sum the forces in the Y, you know what I mean, like legit, we're going to say, hey, we have a P up plus a BY up. That has to equal to 0. So now we know that P is equal to negative BY. So, you know, by convention, we just have all the arrows going in the positive direction. But with shear, we say that, hey, this downward direction is positive. So let's do this. So a free body diagram, we got a negative answer for this. So let's just do something bizarre and then put BY downward. And then let's see what we get for summing the forces. We're going to have P up minus BY is equal to 0. So now BY, and I apologize. This should say BY is equal to negative P. So for this, for that first scenario, BY is the opposite direction. It's negative value. So we know that it's downward. Cool. But then when we do this convent, and we got a negative sign, and that indicates it. You know what I mean? And then when we do this convention of we'll just throw BY down for whatever reason, and we're going to go P minus BY. So now we know that BY is equal to P. So we actually got the direction right. And if we have this convention, you know, it's kind of bizarre because it's downward, but we do get a positive number. And so that's what they're saying. It's just like, hey, by convention, if you do this, which is the downward BY, and then you solve for BY, and if you get a positive number, cool, that checks. That's going to be a positive shear. So that's kind of what's going on here. It's just, it seems bizarre to do that in the downward direction over there. And if you had the other way, if you had a cantilever this way, and then you're chopping, and you have a force here, and you're chopping this side out. Force is here, and now you would have a force up, but we're saying over here, a force up is a positive shear. And so now, what they definitely say to get there faster is if you do a clock, and you're saying this is clockwise is positive shear. Basically, if this force is on the outer perimeter and you turn this into a circle, it's going to spin it in a clockwise direction. So the force downward that does that is positive shear. So now I can just start taking anything. This is a cut face. I do a clock. So if I have an upward force over here, that's going to be positive shear. You know what I mean? And then just the convention. Obviously, the convention for moment's a little easier. If you turn it into a smiley face, that's going to be a positive moment, positive shear. So I guess my analogy of being like, okay, I have this cut face over here, so I'm going to connect the other side to the wall, and then I'm going to drive a Jeep across it, and it's going to look like that. I'm going to get that shape, which has a force that way and this way. And then my convention is like, well, there's two ways you can drive across the cantilever, from left to right, and if you do this from left to right, that's going to be a positive shear. Downward over there, upward over there. If you drive the Jeep from right to left, the molecule is going to look like that, and this is going to be synonymous with negative shear. This could be a good check on reality and a good place to start, but if you're just going for that textbook solution of just like, hey, friggin' A, just give me the answer, this is a good way to do it. So what are we analyzing now? I guess let's just do this. Let's just do this one. So what I'm going to do is I'm going to cut it right there. Cool. I have so I expose this. Draw a circle. Draw a clockwise direction. So downward V is going to be synonymous with positive shear, and then a smiley face M. And then if we do it the opposite, you know what I mean? If I have this for my cantilever, and I have this for my P, and then I chop out anything over here, I'm going to take this. This is my P down. Now this is my exposed face. Draw a circle around it. Do a clockwise rotation. So that's going to be a vertical up is positive. Smiley face is, so there you go. And this is just going to be a lot easier. And then my method was, well, hey, if you cut this face out, that's the face that you cut out. Attach it to a wall. Has to be on this side. And then drive a Jeep over it. Well, you have to drive the Jeep this way, and then you're going to get it downward. And then just by knowing that if you drive the Jeep from left to right, it's positive, right to left, you get a negative convention. So it's just like 10 extra steps to get there, but it's a cool check on reality. I like my little Jeep analogy, because now I can say if I have a downward force over there, that's going to be a negative shear. So it's, it's also a step to get confused too. But no, it's pretty good. And right here, we see that the upward force is a positive shear. So heck yeah. So and then if we're just doing, so now, how does this relate to the free body diagram? Well, you just do. You just chop this out of outer space. You have a P here. You draw your circle clockwise. By convention, I'm going to say, hey, a force is there. It's opposite. Like I said, the BY thing. We usually do BY up, and we want a positive number for that. But actually what we want to do is get this shear in the direction that causes clockwise rotation. And then if we get a positive number on this, we know that we have positive shear. If we get this number as negative, we know that we have automatically negative shear. Same thing here. We're going to put the moment that creates a smiley face. And if this number turns out positive, after we do the free body diagram and moment balance and torque balance calculations, if we get a positive number, we know that moment's positive, we know we get a smiley face. But if we get a negative number for this, we already know that it's negative. So there you go. Just getting quicker for that sign convention, and that will help. So after what I did, for 2 hours or whatever I've been doing, and then reading the text, but I wouldn't have come across, just like the Jeep analogy, which I will now use as a backup plan. I mean, if I just really want to get there, I'll do, like, no one does that either. That's new. That's new probably to everyone. It's just like take the little free body diagram, draw a circle, and then follow the circle in a clockwise direction, go to your cut face, and then put the force, and that's going to be your positive shear. The moment's going to be easy. Hell yeah. Just anything that causes a smiley face. Obviously, that's going to cause a smiley face because you go to the angle and then you bunch up those molecules. So that must mean you're stretching out the bottom, and then the object's going to look like that, smiley face. And then, so that's what also the literature says. Now, the take-home point that we're going to spend maybe just another little bit of time on. Okay, so the other part of this literature, which is crazy because, like, I teach material mechanics from the, hey, if you're pulling on something, you just know it's changing length, right? You know what I mean? So the spring equation is technically wrong. Like if you're going to use this in Excel and then have an origin, have a coordinate system, you have to have a negative x. Like the I'm not going to write it on, I don't want to ruin my card because I like it this way, but the force of a spring is negative k change in length. And then by convention, if you have something actually loaded, you have a force that way and a force that way. Well, guess what? This is what they're saying. It's like, hey, this force is in the positive x direction, but this force is going to the negative x direction. But for tension, we're saying that both these forces are positive. You know what I mean? What we do, I mean, and that's kind of bizarre, but like typically, you know, and this will kind of blow your mind, it would make more sense to do this, even though it doesn't look right now. But if I say this is point A and this is point B, and then I take this bar, and then I say, well, I must have a BX in that direction, and I must have, at this point, an AX in that direction. So now these are both, and then I'm going to sum the forces in the x direction is equal to 0, and I'm going to find that, and if this is the case, I'm going to find that AX plus BX is equal to 0. Well, I'm going to find that they're the opposite of each other. AX is negative BX. So why go through all the hassle if I just know that if I have, I mean, because obviously, chop this in out of outer space, 2 forces on it. Well, hell yeah, now it's going to be, you know, changing velocity even faster. It's just going to be going that way forever until it reaches light speed. You know what I mean? So we have to, if we're observing that this beam isn't moving, yeah, one of these forces has to be the opposite direction. So that's what they say just by sign convention. You know, we're calling this a positive value for this, or a positive value for this side. Either side results in tension. Now, and the same thing is true for compression. You know what I mean? So even though that this one is going in the negative x direction, and this one's going in the positive x direction, we're saying, hey, if we get, well, and this is messed up, because just like you would say, if this is my object, and I'm chopping it out of this side, a downward, clockwise rotation is positive shear, and this is a positive moment. We're saying that, hey, what they want you to get at is if I have an actually loaded member, and you just do this, you know, 100% do P's in that direction, but if I get a negative number from this, and I get a negative number from that, well, it just means that the arrows are swapped. So then you get this. But you don't initially draw it like this, you know what I mean? So if you're going to get technical, the sign convention isn't to draw it like that. It's to always draw things in tension, and then if you get a negative number, then you can know that it's in compression. And there's a way to actually use, so I'm going to try to spend just a little bit of time on this to end the video, because I'd probably want to make a whole video just on this concept of like, well, if I set a x and y coordinate here, and I know we have a, let's say, a tensile force, and my force of a spring is negative k change in length, and I know that this side is going to be this. And so this is where no, I don't think I want to get into this. You know what I mean? This is where this negative sign just drives me absolutely insane. That'll be for a separate video. But it gets complex. Like, just even figuring out if it's negative or positive is just, for me, it just makes my mind melt. So that's why I always just say, well, hey, I know that the force is equal to the spring constant times the change in length. So if I have pulling and tension, well, great, I'm going to have a change in length that's this way. We're going to get more change in length. If I'm pushing in compression, this change in length, you know, whatever that value is going to be this way. So, you know, that I'll have to spend, you know, that would be a 2-hour video for my style just on that topic. But it does go back to that, because they definitely talk, they at least talk about the fact of what I just talked about, is that if you have an actually loaded member, you always do it like this, And then simply, if you get negative values for these, you just know the darn thing's in compression. My tangent on going back to the spring constant, and then just the fact that Hooke's law, there's definitely a lot of practicality of taking Hooke's law and just making the spring constant without the negative, and you just assuming what it's doing, changing length. In what direction, either lengthening or shrinking. Okay, so that's about it. And that was just my addendum of reading the text. I think we came up with a cool thing. Circle your object, figure out where it's circle your object, figure out where it's cut at, go to the clockwise, throw the V in, and that's going to be positive shear. And obviously, the moment that makes a smiley face is positive. All right, hell yeah. So that's sign convention, and I think we did it. So thanks for joining me, and that's a video.